generation, which is published in ICML 2023. And as you know, the video prediction model with short context window, we can use it to generate the long video by a sliding window functions. And we also like the model to predict the temporally consistent video. This means that the same content should be generated if the camera is paying back to previous observed location. In addition, the future prediction on unseen part should also remain consistent. So Briarwood has investigated the technique for modeling the long-term dependencies, such as the temporal hierarchies, the stride sampling with frame-wise interpolation, sparse set of selected frames, or compressed representation. However, they still have difficulty scaling to dataset with many long-range dependency. So first of all, it's limited by the training time because of the recurrence, and it's difficult to scale to complex data. In addition, the transformer-based method over the latent space, they scale very poorly to the long video because they have attention mechanism and it has quadratic complexity. We know that like the long video will contain tens of thousands of tokens. And the method is trained on subset of tokens. They're limited by the truncated backpropagation through time and the naive temporal operation. Also, we are lacking of a benchmark for evaluating the temporal consistencies. The prior world, they either focus on generating the long video in which the short-term dependency are sufficient for accurate prediction, or they rely on the metric that's more sensitive to the image quality rather than focus on capturing the long-range dependency. So in this paper, their contribution has three main contributions. First of all, they propose free video dataset with long-range dependency, including the metric they generated from 3D Sync. They benchmark the state-of-the-art video generation model on the datasets, and they analyze the capability of each in learning the long horizon dependency. And finally, they introduce the TECO, short for temporal consistency. It's an efficient and scalable video generation model that's learned the compressed representation, allow for efficiency training and efficiency generation. So let's get some background knowledge. First of all, the VQ-GAN, which is short for vector quantized GANs. The VQ-GAN is an autoencoder that's learned to compress data into discrete data. It consists of an encoder, a decoder, a codebook, and a discriminator. So given an image, the encoder maps the image to its latent representation, and then the latent representation is quantized by the nearest neighbor lookup in a codebook to produce a ZQ. And then the ZQ is fed to the decoder to reconstructing the original image. The second knowledge is a mask kit, which is the try to model the distribution over discrete token, such as the one produced by VQ-GAN. The mask kit generates image with comparative sample quality to auto-regressive model. by a fraction of sampling cost by they using a mask token prediction objective during training. They, as we can see now, they mask in some token and they try to predict the mask token. I think this a kind of very popular technique in the NLP. The proposed framework of TECO is shown in the figure B, where the X consists of the sequence of video frame. Their primary innovation is designing a more efficient architecture that can scale to very long sequence. For previously state-of-the-art work, they try only a single spatial temporal transformer to model every code, but it will be very expensive if the sequence gets bigger, like tens of thousands of tokens, because of the attention. The take-home design is a design with the intention to retain its high capacity of scaling property and ensure the efficient training and inference. So as we can see here, the take-home consists of 4 components: the encoder, the temporal transformer, the decoder, and the spatial masking. First of all, the take-home, they downsample in space, downsample from Z, and they feed into the transformer, and then they expand it back using the masking, which is applied separately to its frame. So let's break into small component of TECO. In the encoder, they learn a CNN encoder which encodes the current frame condition on the previous frame by channel-wise concatenating. Then they quantize the output using the codebook to produce ZT. This is the loss function, which is take inspiration from the VQ GAN's paper. HG here is a stock variant operation, and this part we can see as some commitment loss with weighting factor beta. The second part is temporal transformer. Like before modeling the temporal information, they apply a single stride convolution to downsample its ZT. After that, they learn a large transformer to model the temporal dependencies and then apply a transport convolution to upsample the representation back to the original resolution of ZT. In summary, the 10 temporal transformer use this following architecture. In the decoder is an upsampling CNN that tries to reconstruct the HT. The ZT here can be interpreted as the posterior time step T, and HT is the output of the temporal transformer, which it has the information about reverse time step. The ZT and HT, they are concatenated channel-wise, and they are fit into the decoder. This loss function is a cross entropy reconstruction loss. This will encourage the ZT to encode the relative information between frames because the temporal transformer output HT is already aggregate information over the time. And we can learn more complex code for efficiency modeling over long sequence. They use a masking to model the prior probability of ZT, even conditional on HT. Using this prior allow not just faster but also higher quality sampling compared to an auto regressive prior. Here is their loss function of this step, and they follow the prior word to sample a random mask MT. and they try to optimize the L file where HT is concatenated with the mask GT to predict the mask token. And the final loss function of Teco consists of the loss of VQ, the loss of reconstruction, and the loss of file. Here is a technique that's innovated by this paper. They propose the drop loss, a simple trick to allow more scalable and efficient training. So as already shown in the figure before, the Teco can be separated into two components. The first is to learn the temporal representation, consists of the encoder and the temporal transformer. And the second component is to try to predict the future frame, which contain the dynamic file and the decoder. We can increase the training efficiency by randomly dropping some time step, and those time steps will be not decoded and omitted from the reconstruction loss. Because the random indices, they are selected in each iteration, like different random. So the model still need to learn to accurate predict all the time step. So this drop loss reduce the training cost significantly because the decoder and the dynamic file, they require the non-trivial computation, and we can reduce this. So the author performed experiments on 4 datasets, and they compare against selected state-of-the-art baseline, like the latent variable-based variation model, autoregressive likelihood model, and diffusion model. They train on the model on the VQ code using a pre-trained VQ GAN for each dataset. Here in this table is the quantitative evaluation on 4 datasets. As we can see, the Teco performed almost the best across all the metrics for every dataset when training on 300 frame video. Here is the result when compared with the space-time transformer method, and Teco also outperformed the similar video generation model that's use space-time transformer. So the key insight we can take from this paper is firstly, the trade-off between the fidelity and learning long-range dependence. So this work finds that the long horizon information can be prioritized through the bottleneck representation, and allocating more computation toward the higher resolution representation will encourage the higher fidelity. Secondly, although the frame quality will saturate very early, the long-term consistency will continue to improve when we have a longer training time. During the training, they observe a very interesting phenomenon that the short horizon metric, they will saturate very early, but the long horizon metric, they will continue to improve until the end of the training. And they hypothesize that this might be due to the likelihood objective, where modeling based from neighbor frames is easier than learning the long horizon bit scattered throughout the video. Okay, thanks for your listening.